So then applying the change of base formula here, we can apply the change of base formula and use a base that's convenient for us to be able to calculate. So if the bases are related, we want to do this without a calculator. However, if the bases are unrelated, we need to change it to a base that we can use to somehow apply our calculator to this. So this one here, the change of base, these bases are not related. So I'm going to change it to base 10 so I can plug it into my calculator, because I know at some point I need my calculator here to be able to calculate a decimal value for this. So I'm going to change base 10, so my log the argument in the numerator, log the base in the denominator, plugging this into my calculator. Now I've used the change of base formula. Now I can actually evaluate this log using my calculator. And I'm getting 3.287. Okay, which sounds about right, because 3 to the power 3 is 27. So we need bigger than 3. That little bit extra gets us up to 37. Okay, so the next one here, log base, we're going to change this to base 10 because again these are unrelated bases. So there's the log of my argument. The change of base formula says I put the log of the base in the denominator and then work that out. Log 1.3 divided by log 6. Okay, I get 0.146. So that's basically a root. So I need to put a root power on 6 to be able to get it down to 1.3. This one here, same thing. Log base 10. Actually, I'm going to use my ln button. So this is base e. Okay, so you might want to try this yourself, because it really doesn't matter what base I use. Okay, and I do have a ln base on my calculator, and regardless of the base I use, as long as I can calculate it, I'm going to get the same value. So I'm going to get ln 45.67 divided by ln 1.3. I get 14.56565. So that's my decimal value. It's approximately to 14.565. Okay, and you should, whether you use base E, base 10, base 3, whatever base you want, this is going to be the same value. Okay, so the last thing we're going to look at is log identities. And log identities is basically like trig identities, where we have to prove that these are true. In fact, these expressions are equivalent to each other. And some of these identities actually are very useful shortcuts if we are allowed to use these. Okay, but we're not using shortcuts to prove identities. So remember, with identities we have left side and right side. So I want to prove that this expression is equal to this, and there's infinite ways to do this. So I'm just going to show one way here. So if I want to make these things look the same, I need the same base. So I'm just going to use change of base formula. So I'm going to log base 2 of my argument, log base 2 of my base, and then simplify this. Well, this becomes 3 log base, oh there it is, there's my base 2x, that's the same on that side, and that's going to be equal to 3. Those cancel out, so left side equals right side. There's my proof. Okay, so these are algebraic, I just have to show this algebraic steps to show that one expression is equal to the other. Now what this identity actually implies is that, notice that if I cube the base and cube the argument, that seems to stay the same. That seems to keep it the same value. And that's a very useful thing if it in fact is true. And I'm just going to write it over here. If I have A and B, what this is kind of implying is that A to the x and B to the x, those are actually the same. If that's really true, I'm going to put a question mark right now. If that's really true, that's a very useful identity. Okay, so maybe we'll look at that later. Okay? You might want to investigate that yourself, actually. So here's another identity. I'll need to show that the left side of this is equal to this side. Again, one of the things is that the bases are not the same. So in order to make the bases the same, I gotta, to look the same, I need the bases at least to be the same. The nice thing about this is, and you may want to decompose this, but this one here is dividing logs. And the only time we see dividing logs is change a base. Okay? So what I'm going to do first is I'm going to deal with the numerator, just make it into one log. So I'm going to use my log properties. Okay, so this ends up being log, and the power goes on the x, and the plus becomes times. So you get log 3x squared. So this is very useful here because now I have exactly what I wanted there. And I end up with log base 3 in the denominator. Well, that's change a base formula. I can just change that to base 3. That's the log of the denominator becomes my base. So there it is. Left side equals right side. Proof. And there's many ways to do this. This is just only one way to do it, but this is a proof of these logs. So this last one here, I've got two logs, two expressions. I got one expression. Algebraically, they just don't match. Here I got base A, base B, base Y. Well, okay, well, we could either change it to base A, we can change things to base B, or we can change everything to base Y. Okay. Let's make this into one fraction. Well, I don't know. Let's see. Let's maybe change this to base Y to start. Okay, we could do anything we want, and they all work as long as we do something algebraically correct. So instead of that, I'm going to start with changing it to base Y. So I'm going to get 3 over log base Y of Y over log base Y of A. So there's my main denominator. I'm going to do the same thing here. Log base Y of Y. And we know that's going to be 1. Log base Y of B. So now we have everything in terms of base Y. This fraction, that's 1. And I'm going to put the fraction in the numerator. So I'm going to end up with 3 log base Y of A minus 2 log base Y of B. Okay? And that's starting to look a bit better. I've got A cubed B squared, yeah, base Y, base Y. Oh, there's my subtraction to get in the denominator. So I'm going to do log base Y of A cubed minus log base Y of B squared. Oh, and there's my last step. I can combine using log properties. Subtraction means I divide the arguments. Left side equals right side. There it is.